invitation and the opportunity to address the group. It's an honor. Thank you. I should mention that I am the co-director of the University of Chicago Center for Elementary Mathematics and Science Education, which is partially funded with royalties from the sales of everyday mathematics. So as one of the principal authors of one of the nation's best-selling elementary school textbooks and as co-director of a center, it's partially supported by sales of those textbooks. I have obvious biases, so you'd be wise to be skeptical of what I say here, as I hope you'll be skeptical of the other speakers. In general, I think there's been too little skepticism of the Common Core State Standards initiative. CCSS is a bandwagon that everyone seems to have jumped on. Such enthusiasm, though common in education, is not very scientific. As the famous Roman orator Cicero noted long ago, by doubting, we approach the truth. So this slide shows children who have just been told that their state has adopted the Common Core State Standards. I share the excitement and fear you can see in these children's faces. My comments this morning center on my hopes and fears for CCSS. I'll begin with some of my fears. My first fear is that CCSS will soon become irrelevant because of the assessment consortia. Once the tests from the two assessment consortia, SBAC and PARC, come into use, or even when what's going to be on those tests becomes public, then what will matter will be what's on the tests. And most teachers in school districts will ignore the underlying standards. And right now, what we're hearing from the assessment consortia is worrisome. For example, both consortia claim to be committed to assessing all of CCSS, the mathematics standards, and the reading standards, English language arts standards too, I'm sure, including the standards for mathematical practice, which describe the higher level outcomes that students are to achieve. The consortia also promised to deliver testing systems that cost approximately the same as current state tests. I don't know how SBAC is going to pull off this miracle, but I would characterize the method PARC is planning to use as the Hogwarts approach to large-scale assessment. That is, as I understand it, PARC proposes using artificial intelligence to score constructed response items that assess these higher-level outcomes. Given the current state of AI scoring in mathematics assessment, this is magical thinking. Given the unlikelihood that PARC is actually going to succeed in using AI scoring by 2014-2015, the first year of mandatory testing, and the likelihood that SBAC's plan is not much better, what seems most probable is either that the standards for mathematical practice will not be assessed, or that they will be assessed poorly. This is my first fear. My second fear also has to do, I'm going to turn that off because you're going to look at that, not me, right? Okay. My second fear also has to do with the assessment consortia. PARC is proposing something they call through-course assessments, which at the elementary grades will be given quarterly. The through-course assessments will be high-stakes summative effect assessments over whatever specific content the PARC folks think makes sense to cover in a particular quarter. I find this proposal worrisome for several reasons. The first has to do with the research basis for the grade-level placement of topics in the school mathematics curriculum. I think the research basis is fairly strong for the placement of topics in grade-level bands, such as K2 or 6-8. This is how both the 1989 Curriculum and Evaluation Standards for School Mathematics and the 2000 Principles and Standards for School Mathematics were arranged. The research basis for placing topics in specific grades which is what both the curriculum focal points and the Common Core State Standards did, is considerably wobblier. But the research basis for placing topics in specific quarters of particular grades is non-existent. We will not be getting a research-based set of quarter-by-quarter recommendations because there is no research upon which to base such recommendations. Instead, we will be getting the current best guess of whoever at Park is writing the content framework, as they call it, for the through-course assessments. Once Park designates the contents for its assessments, we will have a de facto quarter-by-quarter national curriculum, mandatory curriculum, and not just for the Park states, but for the SBAC states as well, since publishers are unlikely to fund the development of separate instructional materials for SBAC states. We will thus have a quarter-by-quarter national curriculum for all states that have signed up for CCSS. Note that whatever placement of topics Park comes up with will be entirely untested. We will have an experimental scope and sequence being tried out on millions of school children. The folks at Park will use their professional judgment to devise something that makes sense to them, and we'd all better hope they're right. But even if the Park folks are right today, they may be wrong tomorrow. Even if Park somehow finds the optimal grade placement for all, quarter-by-quarter placement for all topics, that placement would depend on current instructional approaches. If someone discovers a better way to teach some topic, new approaches and new sequencing may be possible. And such innovations in instruction are not unlikely in our age of rapidly advancing technology. Dynamic geometry software, for example, could make possible radically different approaches to elementary school geometry, approaches that would render obsolete any existing formerly optimal sequencing of topics. The quarter-by-quarter specification of the curriculum Park is planning would severely stifle curricular innovation. But perhaps the strongest reason that these quarterly through-course assessments are a bad idea is that they will encourage what I would characterize as through-course cramming. Currently, in too many schools across the country, test prep displaces the regular instructional program for several weeks before the annual standardized test. Children are drilled day after day for weeks in whatever teachers believe will be on the state test. Now imagine that high-stakes standardized tests come not once a year, but 4 times a year. There will not be 4 or 5 weeks of test prep per year, but 15 to 20 weeks, half the school year or more. Now, as we all know, and as my daughter has often told me, cramming works if your goal is to pass a test. But if your goal is to really learn something, to be able to recall it and use it at some later time, then cramming does not work. As has been found over and over again in more than 100 years of research into spaced versus massed practice. I worry that 4 times a year high-stakes tests are going to reduce the curriculum to serial cramming. Let me mention one more worry before I get to something hopeful. CCSS, as you know, includes both content standards and standards for mathematical practice. When I began to study the content standards for grades K-6, I could not find one piece of the paper and pencil arithmetic curriculum that I studied more than 40 years ago that had been deleted. Now, yesterday, Susan Joe reminded me of one bit of paper and pencil arithmetic that has been deleted, the square root algorithm, which my beloved Mr. Serpy tried to teach me one day in 9th grade in 1965, but which I never really learned at the time because my chemistry teacher, Coach Roach, taught me how to extract square roots with a slide rule. So who needed the algorithm? Well, even with credit for the deletion of the square root algorithm, the arithmetic curriculum recommended by CCSS is roughly what William Brownell might have recommended in 1940. Now, I think William Brownell was one of the giants of 20th century mathematics education. But what he called meaningful arithmetic is not what today's children need. Please don't misunderstand me. I'm not calling for banishing paper and pencil arithmetic from the school mathematics curriculum. I'm simply saying that conditions have changed since I was a child in school, and the curriculum needs to adjust. As Zalman has pointed out elsewhere, today the standard algorithm for most adults who have a complicated computation involves a calculator or other machine. Children do need to learn paper and pencil arithmetic for various reasons. But in designing the curriculum, we should reconsider the particular algorithms to be taught and the degree of complexity of the calculations children are expected to carry out. In choosing an algorithm for today, the optimal balance between efficiency and conceptual transparency is not the same as it was 50 or 75 years ago. Today, it may be better to teach children a paper and pencil algorithm for a particular operation that is less efficient but more transparent. Because if it's efficiency that's what's wanted, then a paper and pencil are not the appropriate tools. The cost of months or years of study of complicated arithmetic procedures is not trivial for many students. As you all know, much of the teaching in U.S. elementary school mathematics classrooms is heavily procedural. Now, most of the people in this room probably like mathematics and were good at it in school. And research shows that students who like mathematics are more likely to learn concepts even when they are taught procedurally as compared to students who don't like mathematics, who tend not to learn concepts when they are taught procedurally. Many children do not by themselves connect the conceptual dots when they are taught procedurally. And they grow up thinking mathematics is a grab bag of procedures that don't make much sense. Most or all of you are also familiar with Li-Ping Ma's finding that many U.S. elementary school teachers do not understand the long multiplication algorithm, don't understand it in the way that you and I mean by understand. As Richard Skemp pointed out in the 1970s, in many elementary school mathematics classroom, I understand means simply I can do it. When the teacher asks her student if he understands the long multiplication algorithm, what she's really asking is whether he can carry out the procedure properly, not whether he understands why it works. Although I realize that the CCSS writers want students to develop real understanding of the algorithms that are taught, I wonder how teachers who don't understand long multiplication, but think they do because they can execute the procedure properly, are going to be able to induce conceptual understanding of that algorithm in their students. I worry that CCSS's overemphasis on paper and pencil arithmetic will undermine attempts to better balance concepts and procedures in school mathematics. So we were disappointed when CCSS called for retention of the entire traditional paper and pencil arithmetic curriculum of 1950. And our disappointment was heightened by CCSS's complete disregard of technology in K-6. But enough of disappointments and fears. I promised hope, and in the time remaining, let me identify one big reason we're hopeful about CCSS: the standards for mathematical practice. When we read the CCSS section on standards for mathematical practice, we were pleased for two reasons. First, the practice standards call for school mathematics to be about more than just facts, concepts, and skills. The practice standards require that children learn to reason mathematically, communicate their mathematical thinking, model with mathematics, solve problems, make generalizations, attend to precision, use tools, and do many other wonderful things not usually required by state standards. This is a big step forward. We were also pleased with the standards for mathematical practice because they helped us get a handle on a problem we'd been having with everyday mathematics. In the 2007 edition of our books, we had introduced a goal structure that specified about 24 mastery goals for each grade. These grade-level goals provided a framework that we used to track instruction, practice, and assessment across the program. And for the most part, they worked fairly well. We made giant wall charts for each grade. Kathleen remembers these wall charts. They were huge. They were as big as this blackboard or bigger. or each one of the sections of the blackboard. We made huge wall charts for each grade that tracked each part of each grade level goal across every lesson of the materials. We noted where we had instruction for each skill or concept, where we had practice, and where we assessed for progress and for mastery. As some of you may know, everyday mathematics takes a distributed approach to instruction, practice, and assessment. So keeping track of where we are is crucially important, and the grade level goals helped us do that. But a common failing of any list of goals, as those of you know who've written such lists, including lists of standards, is that they tend to overemphasize lower level outcomes. The reason for this is simple. It's easier to write goals and standards for lower level stuff than for higher level stuff. Once our third edition was published, we realized we had fallen into this trap. Although we believe that our materials address higher level outcomes such as reasoning, communication, mathematical modeling, and so on, we found that those things were not fully captured in our grade level goals. And since they weren't captured in our goal structure, instruction, practice, and assessment in those higher level outcomes wasn't tracked as carefully as for our lower level outcomes. So we began trying to find a way to capture the higher level outcomes we value but felt were missing from our grade level goals. We'd been working on this problem for some time when CCSS was released. And we soon realized that the standards for mathematical practice could help us. So we set to work to understand the standards for mathematical practice and to figure out how to leverage them to highlight the higher level stuff we long valued in everyday mathematics. We think we have made some progress. We began with a close reading of the practice standards. I don't know how many of you have spent time reading CCSS's practice standards, but I know that we have spent many happy hours with the 8 practice standards. One of the first things we noticed was that they are not written in a way to be immediately accessible to the average elementary school teacher. Consider, for example, practice standard 2. So there's practice standard 2. Feel a little bit like I'm in church, and this is our text. So, all right. So this, we found a lot to like in this standard. Making sense of quantities and relationships, abstraction, connecting symbols to reference, representation, units, and so on. But we thought teachers might be puzzled. First of all, the headline for the standard doesn't seem to fit the text. What most elementary school teachers think of as reasoning, discussing, arguing, making inferences, drawing conclusions, and so on, is not prominent here. Those things are more noticeable in Standard for Mathematical Practice 3, construct viable arguments and critique the reasoning of others. Second, the language here is not entirely transparent. Consider what we found to be the core of this standard, the movement back and forth between some situation and the world of mathematics. The movement from a situation to a mathematical representation of that situation is called decontextualization in this standard. The opposite movement, reconnecting mathematical abstractions and symbols with their reference in the original situation, is called contextualization here. We thought that these two moves, decontextualization and contextualization, were at the heart of this SMP. But we also worried about how teachers would make sense of this. Another tricky feature of the standards for mathematical practice is how they overlap and connect. SMP2, for example, overlaps quite a bit with SMP4, model with mathematics. Like SMP2, this standard involves identifying quantities and relationships in situations, creating representations for those quantities, and reconnecting mathematical objects with the situations they come from. So there appears to be a fair amount of overlap between SMPs 2 and 4. SMP1, which I won't show, is make sense of problems and persevere in solving them. It also overlaps with SMP4, which also involves solving problems. Now, we think these standards are terrific. We are especially pleased to see mathematical modeling elevated to such prominence. But we also wondered how elementary school teachers would make sense of these standards. And it wasn't clear to us how we could use these standards to address the problem I mentioned before, how to bring higher level outcomes into everyday mathematics goal structure. After considerable noodling, we came up with what we came up with was to create a set of what we call goals for mathematical practice. These goals for mathematical practice are designed to operationalize the standards for mathematical practice in a way that elementary school teachers can wrap their heads around. For each standard for mathematical practice, we tried to create goals for mathematical practice that captured the main points in simple, straightforward language. We also tried to reduce the overlap among the SMPs by avoiding overlap in the corresponding goals for mathematical practice. So, for example, for standard for mathematical practice 2, reason abstractly and quantitatively, we created 2 goals for mathematical practice. I think I've got them here. Oh, look at this. This slide is animated. Oh, my God. That's purely by accident, trust me. All right, so there's the 2 goals that we created. These 2 goals are meant to capture what we saw as the key features of the standards for mathematical practice 2, decontextualization and contextualization, in language that would be accessible to elementary school teachers. We argued about whether to list the several modes of representation, all those numbers, words, and so forth. But we decided that what we meant would be clearer if we did include them. We had a lot of fun in a sort of U of Chicago way, parsing the standards for mathematical practice and writing goals for mathematical goals and writing our goals for mathematical practice that captured all the main ideas as we saw them. We eventually came up with a list of about 24 goals for mathematical practice that we think work fairly well. We are now working to integrate these new goals for mathematical practice into our overall goal structure so we can better highlight, track, and assess these outcomes that we value so much. So we were happy to see the standards for mathematical practice and believe they will help us solve a problem that we've really been struggling with everyday math. We also believe they could potentially be transformative for school mathematics. As some of you may know, many in the curriculum development community, the community that I belong to, were not entirely happy with CCSS. I've suggested some reasons for this unhappiness here, and you can find more online in various places. But at this point, the Common Core State Standards are final, and the vast majority of states have adopted them. So while not exactly embracing them, we are dealing with them, we hope effectively. If my fears about the work of the assessment consortia do not come to pass, and if the standards for mathematical practice turn out to be as influential as I hope they will be, then it may be that CCSS will ignite the virtuous cycle of improvement in school mathematics that Sibylla envisions. I think we can all hope so. Thank you.
I don't know. We didn't even talk about it.
Why don't we drive on through? I don't.
Drive on through and then do all the questions at the end?
Yeah. That way they'll forget my.
Okay. Get rid of this. Get rid of this. Of course we want to save the changes. We have no idea what those changes were, but we have saved. I should say that although Andy and I are from the same place, we did not do our talks as together. They were created independently. We did share what we created, but that was it.
Zal actually responded to the prompt that was given to us by Philip, and not quite agree.
Thank you for the opportunity to speak about curriculum and teacher education in light of the Common Core. I've chosen to speak about teacher education. It's a vast subject about which we could easily have an entire conference. At every level of schooling, elementary school, middle school, and high school, we may be educating any one of three populations: pre-service teachers, in-service teachers coming back for general training, and in-service teachers coming back to be trained in a specific curriculum. I assume that the three of us were chosen for this panel because we're curriculum developers, and we've had to educate teachers in our specific curricula. My remarks derive from a quarter century of experience in educating teachers in the UCSMP curriculum for middle school and high school. That's quite different from the teacher education that goes on in our colleges and universities, and that I did for 4 decades at Chicago, where the goal is typically more general, namely to educate teachers to be ready for a variety of curricula, or that focuses on the mathematics independent of school curricula altogether. The education of teachers in a specific curriculum is almost always with in-service teachers, and is very often tailored to a course in a single year. Albeit our materials curricula are much more specific than the Common Core standards, but the similarity is that we want to educate teachers to implement a curriculum in a way consistent with the goals of that curriculum. We work through 3 avenues. 2 are obvious. We work through the teachers' editions and through conferences for teachers that may take place at a conference site or in a school district. The 3rd avenue is not so obvious. We train by what we put in the student edition. While the prose in the student edition is directed at the student, it's far more likely that a teacher will read it than will read the background in the teacher's edition. In the teacher's edition, we try to give some mathematical background not found in the student edition, point out connections with content studied earlier in the year or in earlier years, and where this lesson's content is leading. But we know that many teachers look at the teacher's edition only for solutions to the problems. And these solutions can be found in CD-ROMs and online on publishers' websites. So many teachers don't read the teacher's editions at all. This is unfortunate, but a fact of life. We give alternate ways of approaching the lesson in the teacher's edition. We give alternate ways from what's in the text so that a teacher can adapt the lesson to his or her style and his or her students. But we cannot put there the kind of mathematical background and exercises that's in a college textbook, nor can we typically give a teacher overnight problem sets or reading exercises, and we cannot evaluate the teachers on these. Our training at conferences or in individual school districts has much in common with what I anticipate will happen with non-university in-service training in the Common Core standards. In-service teachers will be teaching something like what they have been teaching, but will know there are some significant changes and will want to know how to deal with these changes. At the same time, they bring their own set of concerns. Some want to see how we think a typical lesson should be taught. Some want training in the mathematics, in the materials that they've not encountered before, perhaps in the Common Core standards in statistics or with transformations in geometry. Some want to know how they can get students to read the mathematics. Some want help in what they should say to parents. Some want to know what they should do with students for students with special needs, such as English language learners, top students, or bottom feeders. I'm not exaggerating the variety of needs. We've had sessions at our conferences on each of these matters. In addition, today's teachers want to know what they can do online without books. But the most common questions teachers have concern 2 general problems: the amount of time available for teaching and the diversity of the student body. Perhaps the most difficult questions to deal with are from the places that don't allocate enough time for mathematics. What can you say when a teacher reports that they have only 35 minutes a day to teach their students? Block scheduling cuts down what a class can cover in a year by about 10 to 20%. But its advocates point to the rich discussions that can occur if you have 90-minute periods every day for a half year or every other day for a full year. With the Common Core standards, the questions may be somewhat different, particularly when the tests kick in 2014-15. We can anticipate that teachers will want advice on how much time to spend on test prep. That is, discussing items like those that might be on the test, rather than developing understanding of concepts. At the beginning of the school year, they will be under pressure to review last year's standards for the students who have forgotten them and wonder if they should spend any time at all on that. In the middle of the year, they will feel they cannot cover all the standards and wonder which can be left out. This will be particularly true at 6th grade, where so many people have commented that there's too much for a single year. But this will happen at many other grades, because although Bill Schmidt's soundbite, a mile wide, inch deep, may apply to some textbooks, our research indicates that it does not apply to most implemented curricula at the middle or high school level. A mile wide and an inch deep arose because the Timms people were agglomerating what was taught in lots of different classes with lots of different materials. It does not apply to most individual classes and thus does not apply to the mathematics experience of most students. Our studies indicate that teachers sit on topics pushing for mastery far longer than they should, not realizing that the mastery often comes when the student applies the ideas in the next topic, or a few topics later in the year, or even the following year. As a result, far too many classrooms are neither wide nor deep. They plow the same land to the same depth day after day. The student is far more likely to experience a proper subset of the desired curriculum, not a superset of it. With regard to students, we can anticipate that teachers will want to know with students who score poorly on the Common Core tests. Should they be put into separate classes? Should an entire class slow down if the scores are not as high as desired? All this is with people using the same materials. This tells us that the curriculum as defined by materials is not the same as the implemented curriculum, no matter how teacher-proof one tries to make the materials. I can confidently say that the Common Core standards are and will be interpreted in different ways by different teachers, and there's nothing that can be done that will keep that from happening. There are those who will view the standards for mathematical practice as the keystones of the document, and there are those who will virtually ignore them. There are school districts that will dictate what teachers should do every day, and those that will give freedom to their teachers to teach whatever they want, as long as the students perform. There are classes in which the grade N standards will be taught at grade N-1, or N-2, or N+2. And others where some standards will not be taught at all. While this may be frustrating, it's a fact of life in a country where there are about 150,000 mathematics classrooms at every grade level. And it is not necessarily a bad fact of life. Teachers whose classrooms depart from what we might want to see present both challenges and opportunities. They tell us where our goals are not clear enough, but also where our goals may be unacceptable or unattainable. They can provide directions for improvement in the next go-round. At the high school level, the appendices to the Common Core describe two pathways. One's called the international and the other called traditional. As a curriculum developer from another project pointed out to me last week, this is misleading because in each pathway there are many possible sequences that could cover the Common Core. Consider the first course in what's called the traditional pathway, the algebra, geometry, algebra pathway. The content may be the same, but the development of algebra in the CME algebra course under the direction of Al Cuoco at EDC is quite different from the development of algebra in the college preparatory mathematics course developed at UC Davis. They're both quite different from the development in our UCSMP algebra. And of course, all of our projects differ from materials developed by commercial publishers. The order of topics, the way in which functions and applications are woven into the development, the identification of the underlying mathematics theory, the connections with arithmetic, geometry, and statistics, and the use of technology vary significantly in these programs. At a conference 2 weeks ago, these programs and the integrated programs were all felt that we could meet the Common Core standards, all of the Common Core standards, if we were only considering the 3 years algebra, geometry, algebra as a group. But we were frustrated, as Andy has pointed out, by the PARCC assessment, people declaring they plan to test 4 times a year. In all these high school courses, some topics are introduced early in a course to be visited later in more depth. The determination of sequence of topics to the bite size of the quarter of a year will undermine the coherence of the mathematics in these programs, a coherent sequence that has been developed through many iterations, often over a period of decades. Indeed, we're all worried about the incoherence that comes from treating standards individually. This is what happened in the 1970s when a similar movement to identify curriculum in detail occurred, the movement of behavioral objectives. Already in many of our nation's classrooms, teachers are asked to write one standard each day on the blackboard or whiteboard, whatever, and teach to that standard. As Andy has already noted, everyone's good intentions are likely to be undermined by these assessments. We have a great deal of experience in these matters. We know what's going to happen. Teachers will no longer ask about student learning of mathematics. They will ask how they can better prepare students for tests. You may believe strongly that tests are a good prod for students to learn more mathematics, and consequently be pleased that teachers will want to know how they can better prepare students for tests. I do believe that mathematics tests serve as a stimulus for better performance for those students who are confident in their ability to learn the required mathematics, for as long as they do well on the tests. So it is likely that tests were great stimuli for most of us in this room. But once a student falters in mathematics, the test is seen as a barrier that cannot be overcome, not as a stimulus to learn. A body of research indicates that students and their parents in the United States are more likely than students and parents in East Asia to view mathematical ability as innate. When a student in Korea or Japan or China or a descendant in the US does not do well on a mathematics test, the message that's received is the student didn't work hard enough. But when a white or black student in the United States does not do well, the student typically feels that he or she simply does not have it in mathematics and gives up. And the parents are likely to agree that they didn't have it either. Teaching to the test rather than to the mathematics is frustrating because the connections and cohesiveness that make mathematics what it is tend to get lost. So when a teacher comes to one of our in-services with the paramount desire to know how our materials prepare students for one test or another, it is rather frustrating. Yet, this is not the most frustrating aspect of working with in-service teachers. The most frustrating aspect is that many teachers of mathematics simply do not know their subject. They have not studied enough mathematics that's relevant to the mathematics they teach. Any advice we offer is distorted by a lens of ignorance. This brings me to some remarks about the pre-service education of mathematics teachers. At the University of Chicago, the education of teachers is at the master's degree level. We have no undergraduate teacher preparation program, though we have a 2-year program that begins in a student's senior year and ends with a master's degree. For students coming to the university from outside, it's a full 2-year master's degree program. As most of you know, we do have a very strong mathematics department and many very fine mathematics majors. Students to the university typically enter as freshmen, already having done well in calculus in high school, with at least a 4 on AB or BC Advanced Placement Calculus test. Yet they are still asked to take calculus at one of 3 levels of difficulty when they're freshmen. Then the typical mathematics major takes a year of real analysis. That's opposed to phony analysis, you understand. So most mathematics majors never see anything but analysis for 3 years of their education. First, their senior year of high school for AP Calculus, then another year of calculus, then real analysis. I needn't tell anyone in this room that this does not give a picture of the breadth of mathematics and the other mathematical sciences. In their junior year, in their junior year, the student takes 2 or 3 quarters of algebra. And then late in the junior year or in the senior year, they may branch out into other mathematics. The University of Chicago's undergraduate mathematics curriculum may be a little extreme, but it is not an unusual circumstance for the best mathematics majors at other universities. Analysis dominates, with algebra in second place. It leaves at least 4 significant mathematical gaps in the mathematical education we would like to have teachers have. Not to mention that a course in the history of mathematics is also quite valuable for a teacher. And so geometry, modeling, statistics, and technology are these areas, and I'd like to take them one at a time. With the Common Core statement that the definitions of congruence and similarity should be in terms of transformations, it's far more than replacing one definition by another equivalent one. By the way, I applaud the Common Core people for this change. It's a terrific change. In fact, the definitions are not equivalent to current definitions. The current most used definitions of congruence and similarity are different for each class of figures for which definitions are given. If you have congruent triangles, you have one definition of congruence, congruent segments, or congruent circles, a different definition for each figure. Having one definition that applies to all figures means that this definition applies to models of real objects and opens up a host of applications. It means that the definition applies to ordered pairs viewed as points in the plane, and thus to the graphs of functions and relations. Before, you couldn't apply the geometry in algebra because there are not too many functions whose graph is a triangle. But now you have graphs, and they can consider those as geometric figures, and you can talk about the congruence of the sine and cosine graphs, et cetera, and so on. And it means that there's a use of matrices other than to solving systems of equations. And students can become familiar with functions in a context in which composition of functions, the identity function, and inverse functions are easier to understand than in algebraic settings. The potential is enormous for wonderful interplays of algebra, geometry, and the real world. And we know this because we have for decades taken advantage of that potential in the UCSMP curriculum. Teaching modeling is not the same as teaching applications. The University of Chicago has a major in applied mathematics, but the courses are not modeling courses. Rather, they study the mathematics that's in the mathematical models, but do not look often at all, or if at all, at real situations that might lead to these models. Modeling begins with a real situation that seeks out mathematics for its resolution. The situation may be as simple as having a number of boys in a class and a number of girls and wondering what mathematics will give the total number of students in the class, or the number of possible boy-girl couples, or the number of possible two-person pairs. That is, modeling can begin in first grade and proceed through the grades. Gradually, modeling becomes more complex, such as in trying to determine the population of a certain species of fish in a lake, or predicting what that population might be years from now. The point is that most teachers have not had a course in modeling, and they need one to understand that mathematical practice. It's not something that just can be done by an hour's lecture at a conference. The situation in statistics is a little more complicated. Mathematics teachers may take any one of 3 kinds of courses. A mathematics course in the mathematics department that tends to emphasize properties of distributions like the binomial, Poissons, etc. Or they may take a course in the statistics department that starts with data and looks completely different from the mathematical statistics course that they might have had in a math department. Or they might have taken a course in statistics as a graduate student in the Department of Education, and that course concentrates on tests and comparison of tests, and they all think that they've had statistics. I've taken a course in statistics so I can teach statistics. It's the second of these that I think would be most valuable. Of course, we like the first as well, but I think you start with the second one. The other courses may appear on the transcript as statistics, but they are not as relevant to the Common Core. At least I don't think they're as relevant. The fourth weakness is in technology. Existing relatively inexpensive technology can be used both to do mathematics and to support the learning of mathematical concepts. We are all familiar with this. Computer algebra systems can be used in calculus and differential equations, as well as elementary algebra. And we have found that they're most useful for the slowest students in algebra, not for the best students. It's the slowest students that are helped most by computer algebra systems, because they see patterns that they've never been able to see with paper and pencil. The algebra system gives them right answers. It's amazing. It's how hard it is to figure out a pattern when half the time you do it wrong. Dynamic geometry software is wonderful in the study of geometry, whether formal or informal. Spreadsheets and statistical software are ubiquitous in the study of statistics. Simulations, explorations, and computer representations are now so varied and powerful that people cannot be expected to learn all this technology on their own. There's certainly enough for a good college course in this stuff, and too few places really are doing that. Simply modifying the mathematics experiences of mathematics majors will not suffice, however. For effective mathematics preparation for teaching will not suffice for effective teaching of the Common Core. The course content knowledge demanded of the teacher requires that we cannot be satisfied with teachers of middle school mathematics whose only certification is in mathematics, is the elementary K-8 certification. The vast majority of students, to put this in international perspective, the vast majority of students in the Shanghai prefecture of China, which is a very special prefecture of China, it's the highest performing prefecture, have mathematics teachers from grade 1 on. This is part of the reason why Li-Ping Ma's sample knew so much mathematics. Those teachers were math teachers for the most part. 90% of them were taught only mathematics. While in the United States, we still seem to think that anything below 6th grade requires a self-contained classroom where the teacher teaches all subjects. And I think there we want to point out that other subjects are as complex as mathematics to teach. Nobody should, the 5th grade teacher is an impossible task to me. We need to prepare many more specialized teachers in mathematics to deliver the kind of mathematics that's in today's curricula. What I'm saying is nothing new. We have at least 20 years of recommendations to strengthen the mathematical preparation of teachers at all levels, but there are too few places where these recommendations have been actualized. For this reason, I'd like to spend the rest of my time speaking about the recruitment of high-quality students into the teaching of mathematics. Part of the problem is that the undergraduate major in many of our elite institutions is designed first and foremost to get students to graduate work in pure mathematics as soon as possible. It's a phenomenon similar to the middle school work to get students to algebra and the high school work to get students to calculus. Along the way, much important mathematics is often given short shrift and sometimes neglected entirely. School mathematics teachers have the responsibility to teach students the mathematical sciences, including statistics and applied mathematics, as well as quantitative literacy, the kinds of mathematics all people, even the non-college bound, need. So there's many places a fundamental mismatch between the mathematics the prospective teacher, or possibly prospective teacher, takes and the mathematics they need. They're educated in mathematics, but not enough in the other mathematical sciences. But even the education in traditional mathematics leaves much to be desired. For instance, many new teachers leave college knowing less geometry than they knew leaving high school geometry, because they studied geometry 7 or 8 years before, and they've never used it since. The simple solution to increase the number of courses a student takes is complicated by state requirements for teacher certification. These requirements differ considerably from state to state, but they share the property that they take potential course time away from mathematics. While we might and probably should bemoan the time taken away, it's testimony to the fact that mathematics education is applied mathematics. That is, it involves not just a discipline, the mathematical sciences, but also a context in which the discipline is used, the classroom. So we should not be surprised that teachers' mathematics, that is the mathematics that was the subject of the previous MSRI conference, the teachers' mathematics involves some different perspectives than found in most undergraduate courses in pure mathematics. The number of mathematically well-prepared teachers depends on, first, the number of mathematically well-prepared students leaving high school, plus the number of students who are not so well-prepared but can be ramped up in college. Then the percent of those who can be attracted to consider a major in mathematics. Then the percent of those majors who become majors. because many fall by the wayside, at least at our university. And the percent of majors who wish to teach then below the college level. We could also consider the number of students who become fine mathematics teachers without necessarily having great knowledge of the subject because they're great teachers, but I'll ignore that for now. Fortunately, the number of mathematically well-prepared students leaving high school has never been as high as it is now. Over 65,000 students scored 3 or higher on the BC calculus test in 2010. Over 92,000 more scored 4 or higher on the AB test, and add 44,000 more if you allow a 3 or higher on the AB. So we have between 150,000 and 200,000 each year, approximately 6% of all high school graduates, who are excelling in mathematics on this criterion. I guess that there's some in the room who would say these are false positives, or there are many false positives in this group, that the advanced placement calculus tests don't really show who's well prepared. You may even offer data based on your placement test that shows that these students couldn't even place into calculus. In our institution, that is, their pre-calculus skills were not sufficient to get them to place out of the pre-calculus course. To that I would respond that their score on the AP test shows that the competences you tested are not necessarily required for success in calculus. And if you don't like that explanation, then you shouldn't have much faith in the Common Core examinations that are to appear, because these are the students who will score well on those tests as well. A study conducted by the TIMSS people in 2000 comparing AP students, our AP students, with advanced math students in a number of European countries found that as a group, successful AP students outscored the advanced math students in all other countries in the study. Yes, it's a biased sample since it consists of the successful students, but it shows that we have a reasonably good supply of good mathematics students. How can we get more of these best students to want to become teachers of mathematics in our schools? That's a question I hope we can discuss at some length in the breakout session on this topic tomorrow. Thank you very much.
Oh, you set me up already. How good. Thank you. I should start out by saying, hi, I'm Paul Goldenberg. I might say thank you for inviting me. I'm not sure that I was invited because of all of the training that we do on our particular curricula. I actually rather bet it wasn't for that, but I don't know what it was. I have to ask you about that. I should start out by saying that the presentation, at least the slides and the way I talk, wander a bit. So I have to say at the beginning that the central message that I want to give is that standards and curricula are not the same thing. We really have a very important new opportunity, or at least I believe that, with the standards. And now what we have to do is figure out the curriculum story. But I'll go on. So science, a bunch of years ago, Al Coco and June Mark and I got inspired by an opportunity that science had that we didn't feel mathematics had. Science is at least two things. You know, it's all of this knowledge about stars and proteins and light and stuff like that. But it's also a way of thinking. And in fact, the scientific method that's taught in school is kind of hokey. It doesn't really include I just blocked on a word, the serendipity that is really a big part of what goes on. You're trying to find the cure for one disease, you're studying some sort of protein, and you know something in your head so that when you see this phenomenon, you say, oh, well, wow, that could actually make a contribution way over here, or it relates to something else. So we get it somewhat wrong, but at least for the science teacher, there were two places to look, even if one was a bit hokey. The stuff to know and the way to act. Mathematics, we were thinking, is also two things, but mostly our texts concentrated on only one of them. There are theorems and facts and procedures and other stuff to know, but this is also a way of thinking, the way of thinking that brought about those inventions or discoveries, depending on what your theory of mathematics is. We call them mathematical habits of mind, and this is a note-taker saver. You can copy down a couple of websites here, and you can go to them, or you can not copy them down and get this PowerPoint off of the MSRI website when I give it to them. Anyway, these are references to some of the papers that we'd written on mathematical habits of mind going back a while. We thought of them as an organizer for curriculum that had two purposes. One was that we didn't not want to in any way water down the content part, the rocks and stars and baboons part of mathematics, because there are some kids who, without that structure, without that information and knowledge, they're handicapped. They just can't go on into fields that require some technical knowledge and expertise in mathematics, and whether that's mathematics itself or science. But while some will need all of the content detail, many don't. I mean, the arguments would be, 5% are going to go on, and 95% of the kids are never going to need to know the Pythagorean theorem, as central as it is to just about everything. Well, that's true, but you don't want to knock it out of the curriculum for that reason, because then that handicaps others. Everybody's going to need the mathematical thinking, and there were examples I won't go through now of why that mathematical thinking that leads to the results of mathematics actually appears in all sorts of other places, even for people who claim they don't do any mathematics at all. Another was the thought that students can learn to think like mathematicians, though obviously with suitable content. They're not going to be studying Banach spaces in second grade, but they can actually be thinking like, doing the kinds of things that mathematicians do when they're doing real research. So we were delighted to see that the CCSS is also two-dimensional. It's got a content set, which is the body of knowledge, the rocks and stars and baboons, and it's got this mathematical practices, way of thinking and investigating, and the educational challenge is actually to take all of that stuff seriously. So one of the problems that we thought about, I'm trying to get back to where I start, which is as curriculum developer, materials developer, is that while the content standards, the content part of CCSS, may differ in detail from the balkanized version of education that we used to have, the form is familiar. As Bill was saying last night, sort of by the time you get down to listing things, it looks like a list. So we could quibble with details of this list. Actually, I quibble with very few of them. Although some, because it's not possible not to, I think. But it would be very easy for that to take hold because it's so familiar in form. This other thing, well, it isn't actually new. I wrote that it's new because we've had vague hints. NCTM had process standards. We've been talking about, these papers that Al Coco and June Mark and I wrote. That was two decades ago. We started that, and 15 years ago that it was published. But in some sense, they're really new because there haven't been the common agreement and the common testing to give them any kind of teeth. Okay, so here's this problem, and this was a problem that both of the prior speakers spoke about before. Teeth hurt, and they help. I mean, I was actually just a moment ago saying this gives me hope that this might actually be, for the first time, a time that we take that stuff seriously. So let's take a look. The reward, I actually don't have a problem with tests or measurement. I really do have a big problem, witness my question this morning to you, Catherine, with punitive the high stakes, because what it does is it forces people to focus only on what it says. And as Andy had said earlier, if we, once the tests come out, whatever they are, good or bad, once the tests come out, it will be a direction that an awful lot of people focus. They won't be asking themselves, what did the standards mean? How do I teach well? They'll ask, does this curriculum match that thing? And I'm doing that thing. So I don't have to say anything about that. You just read it. This one means Diane's comment, well, I heard last week that was really much more comforting than the things that I heard the weeks before. Diane's comment last night, if the test developers are in fact being advised by the Common Core folks, so fidelity to the ideas, and by mathematicians to make sure that the mathematics is not screwed, and by educators to make sure that the items actually make sense, it would be very nice if that all works. And we'll see. So these are two different sections, the content standards and the process standards. I guess, again, because we were immersed in all of this mathematical habits of mind thinking, I'm thinking of these as being usefully distinct, but they're not distinct learning. So here, content, well, how would we like to do it? We often think of the way we're teaching this, that is the mathematical practices, as being the right thing to do while what you're teaching is the content. I mean, it's as if it were exhortative. You teach this way because it's the right way to teach. I'm telling you. I would like to think of it somewhat differently, that the content, which we need to teach in order not to mess up the kids who want to go on in mathematics, the content becomes a vehicle for mathematical ways of thinking. So you can't teach mathematical ways of thinking without teaching something, and so that's where the contents are. You don't want the content to be appearing out of the blue in the books. This is the way it's done because that's the way it's done. You would like it to be reflecting mathematical thinking. This, by the way, doesn't mean that students have to recapitulate all of the history of mathematics and discover everything. So, lest anybody thought I said that, I didn't. The other way around, the mathematical practices are an organizer for content. So there are a lot of stories that you could tell with the same. Every novel is about love and power and generosity and hate and greed and avarice and all that sort of stuff. All the novels are about, those are the basic things in every single one. But the way you rearrange them tell lots of different stories. Ditto mathematics. You can take the same content and arrange it to tell a history of mathematics story, or an application story. Apply that, all of this stuff is organized around applications, or some kind of ladder-like structure, or something else. And what we had been thinking all along, and I would like to recommend for us as a way of interpreting the Common Core standards is the story that you're telling is how mathematicians think. And you can keep the same content or different content, there are, but you can keep the same content and tell that story instead of some other story. Actually, one of the commonest stories is, here are 400,000 things to know. So, but that's not a very good story. So I said that already. I scooped myself. Actually, you scooped a whole lot of me last night. You'll see a bit of it. So again, this is the core. Standards is not the same as curriculum. By the way, that's not the same as teaching, but I won't be talking about that so much. A whole lot of thinking went into the standards. Bill talked about that. I mean, right down to which words were chosen for things. But it can't all be captured in list form. I mean, by the time you've taken a debate or a presentation or a whole lot of thinking of a bunch of people working together, and you've written it down in a form that anybody can read, you've lost most of the nuance that went behind it. And you either have to recapture it by saying, you know, what does it mean to understand? What about understanding? Don't you understand? So there's this list problem. So I want to talk about the terseness that results. I'll give an example from the Texas TEKS. This is actually July of 2010, but we faced this a whole bunch of years ago when we were developing our elementary curriculum, and we had to... development of curriculum, by the way, you're really very careful about the mathematics, or at least we are. You're really very careful about the psychology, the cognitive stuff. You watch kids to make sure that they are enjoying this and engaged. You watch teachers to make sure that they can handle it. And then there's the whole bunch of politics. So here's one. In order to get it out through a publisher, you have to make sure that Texas will buy it. So multiplication, one of their 5th grade standards is multiplication no more than 3 digits times 2 digits without technology. So now let's think of this not as a constraint, but why would anybody have written down the constraint, no more than 2 by 3? Well, what they were trying to do was prevent curricula that have us practicing for pages, multiplying your telephone number times my telephone number. There's no point to that. So they're saying, for the sake of learning this structure, we don't need a lot. And then, by the way, you know, many problems do require more complicated calculus. For God's sakes, whip out the calculator. I might also say, this is actually in response to a comment, now I don't remember which, I think it was Andy, earlier. The role of algorithms has changed. It's not just a matter of selecting the algorithm. The role of algorithms has changed. We used to need algorithms in order to get answers. I mean, whatever else they might have contributed to our understanding of mathematics. Now we don't need them for answers, but we may, again, not want to be throwing them out because we don't need them for answers, because they may serve another role. And I happen to think that well-selected and properly built, the algorithms are a really nice way of showing properties of mathematics. And not all of them. We can do without some of them. But that's not an argument I wanted to get into. So here's this story. You understand why they made the restriction. And they're also saying, by the way, the kid should be able to do it. Well, actually, it's funny. They don't quite say that, but never mind. They say using multiplication to solve problems and don't really tell you that they should know how to do it. But that's not the effect that the standard had. We knew that in building a curriculum and teaching the multiplication algorithm, we'd like to be able to say 600 times 300. I mean, you need that before you can say 637 times 25, which conforms. But 600 by 300 doesn't conform to this statement. Well, actually, we know that it does. Texas wasn't being stupid. Very thoughtful people wrote that thing. Our publisher also knew that that didn't rule out 600 times 300. But our publisher was really worried about the neurologically damaged slug who would be on some kind of adoption committee and would look at this and say, it doesn't conform. 600 times 300 is wrong. This curriculum is out. So they're now trying to struggle. They know that this is the right thing to do. I'm even talking about the publisher. Publisher knows this is the right thing to do. The publisher knows that it isn't ruled out, and it isn't intended to be ruled out in Texas. But the publisher has to be able to sell the book. So they're trying to figure out what to say to us in order to make it possible for them to publish our thing and sell it in Texas. So back to curriculum and standards not being the same, by the time you've written a standard, you're somewhat at the mercy of the interpreter of the standard. So the thinking behind the standards requires unpacking. Bill actually referred to that last night when he was saying that over time you have to come to understand what these words mean, and you have to use it. And one of the big hopes of the Common Core standards is that since it's common, since you don't have to deal with a balkanization of 50 different sets or standards, actually we had 49 sets. I think Iowa didn't do it. But then you had the NCTM and you had a whole bunch of other things to do. So if we only have one thing, we might actually be able jointly to unpack them. I had a different image. First of all, the unpacking is a little complicated and by the time, yes. Anyway, it's also the case, and it was my first... Yeah, that's right. And worse, I have my interpretation, you have your interpretation. Okay, but in building curriculum, there are some places where you might have to do things that don't look like the standards, but are. I mean, you're intending to support this thing, but you have to do something that looks a little different. And in some cases, it might even look like it's rebellious. So I'm thinking, in order to achieve the fraction standards of grade 4, I don't want to teach fractions earlier than that. Actually, I'm very relieved not to have to do some of the things that we were forced to do in the curriculum that we built, except for half. Because half actually grows with the children, and they have lots of ideas. In fact, they even have lots of very correct ideas about half. They know its placement in a sequence, because they were 4.5, and then they were 5, and then they were 5.5. And in fact, they're not using it as parts of pies. They're using it along the number line, their age number line. So there are a lot of things that you can draw from children that would look like they're in defiance or not quite part of the standards that you might have to do in curriculum in support, not rebellion against.
The particular ones in the grade 1 geometry standard, half.
Yeah, half. Although the fact that you said it's in geometry makes it a different thing. I mean, yes. And kids also have that too. By the way, the kids come into kindergarten. We all joke, my half is bigger than your half. I mean, so they don't quite know it, but they know that half is supposed to be equal, and it's evidenced by their having said that. So they have kinds of, they sort of have it and they get refined, but we're not using some of that. Anyway, so I like to think of this as kind of, I think I'm getting that. Is that right from political science, the right term? Interpreting the Common Core standards, you'd like to be an active process. Over time, by all, in the short run, by the way, the handout is really not a handout for this presentation, but for tomorrow's discussion of elementary. Somebody was talking earlier about the need of, to interpret. Actually, that's right. You were saying that you did for everyday mathematics an interpretation of the elementary level. We've been trying. I tried to get a somewhat generic document, but it was not, and that's handed out, and it's online here, if you want to see too. But that's not intended to be. It's intended to be generic, but it's not intended to be permanent. This is still, an offering so that we all get to discuss the thing. Huh? Why did I put the Talmud up? Because the page is pretty. Well, also because you have some. I'm used to being in a position where I can at least cast a shadow there, right? Where is this coming from? Anyway, no, the idea is that you have some little kernel that's been abstracted from something else. And then you have all of this commentary that's wrapped around it. And you don't actually understand the kernel until you get all of this stuff. By the way, some of those little notes out on the side, they're actually references, like footnotes. I mean, this is a very old document, but it has all of that. Anyway, oh my gosh. See there? This is a chapter title here, and there's a statement of a rule, a law, and then there are questions about why that, and this is one set of commentaries, and there's another set of commentaries. And these are commentaries wrapped around the commentaries, and these are little footnotes. And okay. Did that help? Okay. Anyway, thank you. Thank you for your question. So.
I have heard, and I wonder if somebody could respond, that the Common Core standards were supposed to tell us more or less when the kid should finish understanding something, but they weren't supposed to tell us in what year the kid began or ended the process of understanding that something. And that's a distinction which many of my colleagues haven't heard, and I wonder if somebody could straighten me out.
Let Bill answer that.
I just answered it. I said she's right.
Yeah. Actually, that's the very thing that I was referring to with the fractions and stuff like that. And the only problem is whether people will look at it as in fact Texas did, and say, if you do something before time, we thought we were doing a great job, that we were beating their standards. And
that is a critical
and-
issue for understanding how to use that document, if it's going to be used well or badly.
yeah.
Let me comment also on that. There are people who are not interpreting it that way. And they're particularly looking at the notion, the mile wide, inch deep, and saying, these are supposed to be taught that year. Wasn't that the whole idea of the Common Core? Yeah. But the publishers that I've talked to, and I'm not talking about everyday mathematics, but the publishers that I've talked to say there is no way that they will not have stuff the previous year and so on. The teachers expect that to be there. The mastery doesn't come that quickly for a whole variety of reasons. Now the question is, when you have something like the fraction stuff, which has been delayed, right? My understanding, some of the fractions, some of the things have been delayed. Whether they will now be de facto done the previous year, what will happen to them? Because the teachers are accustomed to teaching them an earlier year. They might want to introduce them anyway that earlier year, and my guess is are they going to want mastery? Well, who knows? Yeah.
Yeah, well, we were under a lot of pressure, a lot of different pressures to do lots of different things. There are some mastery standards that I think are sort of clearly mastery standards. There are 5 fluency standards that are sort of pegs at certain grade levels. By this grade level, you should be fluent with this. And I think a curriculum designer might well make the decision that you need to build up to that fluency over a number of grade levels, and not just sort of suddenly, bang, hit them with it in the grade level where fluency is required. I think there are other standards where the fractions one is a good example. Grades 1 and 2 are really mostly about developing fluency and understanding with addition and subtraction, and fractions sort of creeping in there would distract from that focus. Standards, traditionally state standards, have served lots of different purposes. One of which is to just be a statement of what kids should know and understand and be able to do, one of which is a sort of a framework for assessment developers, and one of which is a sort of guide to curriculum and teaching. That's the sort of stick the standard of the day on the blackboard mentality. We really decided that the standards were just going to serve the first purpose, which therefore puts more demand on intelligent and wise interpretation and implementation of them, because we haven't specified and pegged things down and broken them up into the bite-sized pieces of equal grain size. That was the tradition of that genre. That seems to have been bureaucratically required in previous state standards, but has resulted in this sort of incoherent mess. So there's certainly a greater demand, I think, with the Common Core on the community's interpretation and sort of developing some wisdom of practice in that interpretation.
Go ahead, Diane.